Hi, I am Likita MP from EC6M and my topic is hardware software co-design. Each and every embedded system will be having an electronics which will have both the hardware and software in the design, in which part hardware can be implemented or in which software can be implemented, what are hardware requirements and what are software requirements. So how can we design hardware and software simultaneously can be seen now. So here in this block diagram, first system description, it describes the process and functions, and second hardware software partitioning, and and we have to co-synthesize design hardware, what are requirements of hardware and how have to design, how to interface and all those things. And in software, what should be data size and what should be memory size and all the things need to be designed, and we start to develop all those three. So software development will be working on software development and hardware development team will be working on hardware development. There should be interfacing between should be interfacing team which periodically monitors whether this software or hardware and whether this hardware is compatibly connected together in order to achieve final result. And suppose if there are any changes are required, then we have to go for hardware software partitioning. So here it shows hardware software design. So here in traditional embedded system development approach, the hardware software partitioning is done at an early stage. Engineers from the software group take care of the software architect development and implementation. Various engineers from the hardware group are responsible for building the hardware required for the product. There is less interface between two teams and the development happens between either serially or in parallel. Engineers from the software group take care of the software architect, like uh, what will be database or what is data size, all those things. Once the hardware and software ready, the integration is performed. The increasing competition in the commercial market and need for reduced time to market the product calls for a novel approach for embedded system design, in which the hardware and software are co-developed instead of independently developing both. During the co-design process, the product requirements captured from the customer are converted into system level codes or system level needs or processing requirements. At the part of time, it is segregated as either hardware requirement or software requirement. Instead, it is specified as functional requirement. The system level processing requirements are then transferred into functions which can be simulated and verified against performance of the functionality. The architecture design follows the design, and it goes like this: the partitioning of system level process requirement into hardware and software takes place during the architecture design phase. The architectural design results in the detailed behavioral description of the hardware requirement and the definition of the software requirements required for the hardware. The processing requirement behavior is usually captured using computational models. The models representing the software processing requirements are transferred into the firmware implementation using programming language. The fundamental issues in hardware software co-design The fundamental issues in hardware software co-design are selecting the model, selecting the architecture, selecting the language, partitioning system requirements into hardware and software. Selecting the model is in hardware software co-design. Models are used for capturing and describing the system characteristics. Model is a formal system consisting of objects and comparison rules. It is hard to make a decision on which model should be followed in particular design. Most often, designers switch between a variety of models from the requirement specifications in the implementation aspect of the system design. The reason being the objective variables with each phase. For example, the specification stage only the functionality of the system is in focus and not the implementation information. When the design moves to implementation aspect, the information about the system component is revealed and designer has to switch to a model capable of capturing the system structure. Selecting the architecture is nothing but a model only captures the system architecture um, and does not provide information on how the system can be manufactured. The the architecture specifies how a uh, system is going to implement in terms of number and types of different components and in interconnection among them. The controlled architecture implements the finite state machine model using a state register and two combinational circuits. The state register holds the present state and the combinational circuit implements the logic for next state and output. The finite machine data path architecture combines the controller architecture with data path architecture. Complex instruction set computing means a CISC architecture uses an instruction set representing the complex operations. It is possible for CISC for instruction set to perform a large complex operation with a single instruction. And one more is the reduced instruction set computing architecture uses instruction set representing simple operations. It requires the execution of multiple RISC instructions to perform a complex operation. The very long instruction word architecture implements multiple function units in the data path. The very long instruction word architecture implements multiple functional units in the data path. The VLIW instruction package are one standard instruction per functional unit of data path. Parallel processing architecture implements multiple concurrent processing elements, and each processing elements may associate a data path containing a register and local memory. A programming language captures a computational model and maps it into architecture. There is no hard and fast rule to specify the language should be used for capturing this model. A model can be captured using multiple programming languages like C, C++, Java, etc. for software implementations, and languages like VHDL, System C, Verilog, etc. for hardware implementations. Partitioning system requirements into hardware and software. From implementation perspective, it may be possible to implement the system requirements in either hardware and software. It is a tough decision making task to figure out which one to opt. Various hardware software trade offs are used for making decision on the hardware software partitioning.